Hello everybody, so let's look at a few example problems on exponential functions and their applications. Right? So basically an exponential function looks like this, right? So the standard form of an exponential function is y equals some constant a times b to an exponent. Okay. Now this can be adjusted, right? If you want to do vertical, horizontal shifts, stretches, things like that. But this is the standard exponential form. So what's different between these kinds of functions and the ones that we've looked at so far is that your variable is in the exponent. So the base is a constant and the variable is in the exponent. Up to now with polynomials, rational functions, the variable was the base. It was like x squared or x cubed or square root of x, which is x to the 1/2. But in this case you have x up here. Okay, so this kind of introduces the need for different kinds of techniques in order to solve graph these kinds of functions. Okay, so this first example right here asks us to put the equations in standard exponential form. So an exponential function can be expressed in different ways. They're equivalent. Sometimes you can change the bases, sometimes you can sort of have stuff in the exponent, or you can have the exponent be x only. Sometimes you can have a positive exponent, sometimes a negative exponent. So you can have like equivalent ways of writing the same exponential function. But if you bring it back to the standard form, then you can sort of see or compare the different forms of the function, see if they're the same or not. Okay. So this first one, y equals 8 to the 3x, we want to put this in standard form, and notice that this exponent is 3 to the x rather than the x alone, which is you need for the standard form. So to put it in standard form, basically you want to write this as 8 to the 3 to the x. Exponent rule says that if you're raising a number to an exponent and then again the exponents multiply, so you just sort of separate them like this to get the 3x, right? And then you do 8 to the 3, this is 512 to the x power. Okay, so this is in the standard form. So notice it's the a in front, there's no number in front, which means like a is 1. And then the number that's raised to the x, the base is equal to 512. Alright, let's look at the next example. Y equals 7 1/2 2 to the x minus 1. We want to put this in standard form by, we want this exponent not to be 2x minus 1, we want it to be just x. Okay, so we have 7, let's separate. This is 1/2 to the negative 1 and 1/2 to the 2x. Right? Exponent rule says that same base, different exponents, they will add. We're subtracting in this case because we have a negative exponent. So this is going to give us 7 times 1/2 to the negative 1 is just 2, the reciprocal, 2 to the 1. And this one to absorb the 2, you want to do 1/2 to the 2 and then to the x. So this is going to be 14 over here. 1/2 to the 2 is 1/4 to the x. Right? So we got a standard form. This part is the a and the 1/4 is the b. So it's in the form a times b to the x. Alright, so here is a application of exponentials with a piano keyboard with the notes on the piano. So piano frequency range. So sound wave will cause your eardrum to move back and forth in the case of a so-called pure note, this motion is modeled by a function of the form d is a sine of 2 pi ft. Right, so this is a trig function, and we'll probably look at this in one of the later chapters. In this chapter, in this example, we're going to look at how the frequencies are related to each other. So in this equation here, 2 pi, the f is called the frequency of a note. And t is time. So frequency is basically how many times does the sound vibrate in a second or an hour, kind of depending on what many units or per minute. Okay, so its frequency is kind of the speed of the oscillation, the speed of the sound wave. You can see that it's like this 2 pi f times t. It's kind of like rate times time. All right, so, but this is kind of applied with sound waves. All right, so we're not going to do trigonometry. We're going to concentrate on that f part and how the frequencies on the keyboard are related to each other. All right, so this frequency is called, it's usually the units for frequencies are hertz. All right. The A in this equation is the amplitude of the wave, and this is the loudness. So how loud is the sound that you're hearing? So a person can typically hear sounds ranging from 20 hertz to 20,000 hertz. And they say, well, research says actually that as you age, that frequency narrows. So young people hear higher frequency, and older people stop hearing those higher frequencies. That's like an interesting factoid in there. All right, so let's look at this piano keyboard. So the white keys are labeled A, B, C, D, E, and F. Right, so this is called the middle C. Right, so this is kind of, if you play piano, can you rest your sort of fingers sort of on the middle C? That's a good starting place. A, B, C, D, E, and F, and G, and they repeat. So each of this sort of group from A to G is called an octave. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, and then it repeats. You have an octave. The black keys fit into the sequence as sharps. So you have the F sharp, G sharp, A sharp. So it's kind of in between notes in there. So you have 12 keys in total. If you're looking at a sequence, you have like A sharp, B, C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, and then the sequence repeats. Okay, so there's like a 12 notes squeezed in that sequence. So the piano keyboard is commonly tuned according to a rule requiring that each key, either white or black, has a frequency 2 to the 112 times the frequency of the key to its immediate left. All right, so 2 to the 1 over 12 times the frequency of the 1 to its immediate left. Okay, so as you're going on the keyboard, if you know the frequency of one of them, in this case I know the frequency of the A key. So let's say A is set to be, the frequency is set to be at 220 hertz. Then as you are moving to the keys to the right, then you have to multiply by 2 to the power of 1 over 12 to get this, the frequency of the next keys. And again, so you're going, you're including the black keys in here too, okay? All right, so since there are like 12 keys in a sequence, if you kind of have the starting key on the keyboard here, and if you multiply this by 2 to the 1 over 12 times, then you end up with the 2. Okay, so by the time you go to the next A, so this A is right here is 220 hertz. By the time you get to the next A on the keyboard, this one is going to be twice the frequency. So this is going to be 440 hertz. All right, and by the time you get to the next one, multiply that by 2, this is going to be 880 hertz. All right. If you kind of go backwards, right, that A key had to be 110 hertz in order to, if you multiply by 2 to work this out. Okay, so you can find the frequency of those sort of beginning keys, the beginning A's in each octave. So yeah, two keys, those A's, they're said to be an octave apart. But we can also figure out the frequencies of everything else, right? So let's say I want to figure out the frequency of this A sharp here. Okay, so the one right to the right of that middle A. Okay, so the A sharp next to it is going to be 220 times 2 to the 12. Okay, so let me do that calculation. So that's 233.08 hertz. All right, let's say B. This is going to be the previous one, 233.08 times 2 to the 1 over 12. Which is 246.94 hertz. If I want the frequency of the middle C, it's going to be 246.94 times 2 to the 1 over 12. Which is 261.63 hertz. Okay. Now we don't have to sort of calculate in sequence, right? If I want to figure out the frequency of like any one of them, we just have to count how many away from that original A it is, from the one that we know. Okay, so for example, if I want to figure out the frequency of D sharp, this is going to be the 220 hertz times 2 to the 1 over 12, and you have to see how many keys to the right of A that D sharp is. So we have 1, 2, 3, 4, 5, 6. So it's 6 away. So this is going to be 220, 2 times 6 over 12, which is 1/2. Right, so 220 times 2 to the 1/2. This is 311.13 hertz. All right, cool. So this was here's an application of exponential to music. I don't know that much about music, so if you do, and you hear me talking and saying Not sure if she knows what she's talking about. I don't in terms of the music, but I know how to multiply exponentials. So I found this really interesting because we do have a little keyboard in the house that the kids like to play on. And it's interesting to kind of see how the frequencies are related to the way the keys are set up on the board. All right, I hope this helps you do the homework problem that has to do with calculating frequencies on the keyboard. All right, that's it for this example. All right, let's look at this next example. A computer industry spokesperson has predicted the number of subscribers to GetOn.com, an internet provider, will grow exponentially for the next 5 years. Assume the person is correct. If GetOn.com has 100,000 subscribers after 6 months and 750,000 subscribers after 12 months, how many subscribers will there be after 5 years? All right, so we're going to assume this is an exponential model because we're doing it exponentials. Let's kind of tabulate our information, make a little table. Oh, it does say exponentially. Okay, so that word is mentioned there for the first 5 years. So after 6 months, so we have the time, 6 months, subscribers, $100,000. All right, and then after 12 months, 750,000. So we need to build an exponential model from here. So we know the standard exponential model is y equals a times a base to the x. So, and let's make that x into a t because we're talking about time. And we could either sort of leave that as y, or we can make that as s of t, s for subscribers, and it changes as time goes by. Okay, so we're going to plug in these values one by one because we need to find these constants. We need to find a and b to get our model. So we're going to plug in the first point. So 100,000 subscribers equals a times b to the 6. And we're going to plug in our second point. 750,000 subscribers equals a times b to the 12. All right. Now we have to find a and b. So a good strategy for doing that in this case is to divide these, because if we divide them, then we can cancel out the a. So I'm going to divide. I'm going to do 2 divided by 1. Because just for convenience, all right? Basically because the numbers in 2 are bigger than the numbers in 1. You can divide 1 by 2 also. It doesn't really make a difference. So we're going to have 750,000 divided by 100,000 equals a times b to the 12 divided by a times b to the 6. A cancels out. So that was my goal, to get rid of one of the variables. So instead of like solving for one and plugging in the second equation, which you usually do with non-exponential equations, I mean, that would have worked here too. This is just a little quicker. All right, so 750,000 divided by 100,000, we have 7.5 equals, and now b to the 12 divided by b to the 6, this is b to the 6, because we subtract 12 minus 6. All right, so this will help us figure out our b. So b equals 7.5 to the power 1 over 6. All right, so let's do that calculation. This is approximately 1.4. All right, so that finds our b. Now we can figure out a. So we can go to any of these equations. Let's go back to equation 1. So we have 100,000 equals A times B to the 6, 1.4 to the 6, but we know B to the 6 was 7.5. So we just plug that into here. Okay, so A equals 100,000 divided by 7.5. Which is equal to 13333.3 repeating. All right, so we're going to put our model together because we have our A and B. So the number of subscribers equals 13,333 and a third. Our B value, 1.4 to the T. All right, so this is an equation for that, for this model. Now, I'm going to give you another way to write it just to kind of show the differences of how you could do it. So instead of solving for B here, you could keep B to the 6. So you can say B to the 6 equals 7.5. So you write S of T equals 13333.3. We have B to the 6 is 7.5. But because this was B to the 6, you want to have this as T over 6. So that B to the 6 over T to the 6, the 6's cancels out and you get to B to the T that you need. So sometimes there is an advantage to doing that, kind of showing that it's like every 6 months this is what's happening, because basically the information was given every 6 months instead of every month. But these are essentially the same because in order to rewrite this in standard form, you have to do 7.5 to the power 1 over 6, which is what we did here. That's how we got the 1.4. Okay, so either format is fine. Sometimes you'll see it in one, sometimes you'll see it in the other. Now our question is how many subscribers will be after 5 years? All right, so 5 years equals 5 times 12, which is 60 months. All right, so we got to plug it with this S of 60, 13333.3 repeating, times 1.4 to 60. All right, let's see what that is. Times 1.4 to 60 gives us, lots of subscribers. 7.8 times 10 to the 12. All right. So that's like, what's 10 to the 12? 10 to the 6 is a million, 10 to the 9 is a billion, 10 to the 12 is a trillion. That's, company is very hopeful. The models work, there's limitations, right? So it's always a danger to kind of predicting too far away in the future because things could change, right? Like a company like this could be getting an increase in subscribers at the beginning because it doesn't have any subscribers, so it kind of increases fast. But then at some point it levels off because lots of people already signed up or are interested, so the kind of rate of growth, it will level off, it will decrease. At some point in the near future, we're going to talk about logistic growth, which includes that leveling off. There's like a top limit that can be achieved, like you run out of people, right? With internet or out of people, period. But with this kind of an exponential model, this is what it predicts. So you can kind of go, is this realistic? Use your judgment. All right, let's look at this next example. At birth, your Uncle Hans secretly purchased a $5,000 savings bond for $2,500. The conditions of the bond state that the U.S. government will pay a minimal annual interest rate of 8.75% compounded quarterly. Your uncle has given you the bond as a gift, subject to the condition that you cash the bond at the age of 35 and buy a red Porsche. On your way, I wish I had an uncle like that. Anyway, on your way to the dealer, you receive a call from a tax accountant informing you that a 28% tax on the capital gain you realize through cashing in the bond. The capital gain is the selling price of the bond minus the purchase price. Before stepping onto the showroom floor, compute how much cash you will have on hand after the U.S. government shares in your profits. All right. Let's see. So we need to figure out how much the bond is worth. Okay, so according to our formula, let's see, we're given the initial value of the bond, which is $2,500. I'm not sure what this $5,000 is all about. Okay, so this is, I'm not sure if this is kind of a type of bond or something. I don't know that much about bonds, but this is like the initial value. This is P0. P0. Right. Then this is an interest rate. So this is R, and we need to change that to decimal. So 0.0875. And it's compounding quarterly, so N equals 4 times a year. Okay. And 35. So this is the number of years. T equals 35. All right. So according to our compound interest formula, the amount that you have is going to be the principal 1 plus R over N to the NT. So 2,500 is the principal, 1 plus 0.0875 divided by 4, and 4 times 35. Okay, so plug that in your calculator and figure out how much money you would have. To the power 4 times 35. All right, 51,716.42. Okay, so if your uncle never did this for you, invest $2,500 for a newborn or a young niece and nephew that you have, and $2,500 if you can get a good interest rate. Then by the time they're 35, they can have about 50 grand. All right, so you need to pay tax on this. Okay, so tax. So the tax is 28%. So you gotta find 28% of this and subtract it. All right. Alternatively, it means that you get to keep 72% of this amount. So the government gets 28%, you get to keep 72%. So if you do 0.72 times $51,716.42, this is the amount that you get to keep to buy that Porsche. So this is going to be $37,235.82. Still not a bad amount to buy a car. Maybe not a Porsche. I'm not sure how much Porsches are. There you go. That's it for this problem.